Hi everyone, welcome to our presentation with Project Group 7. Our team members are Alexa, Maxime, Sammy, and I'm Rajid, and today we're going to present to you our research on in-body backscatter communication. Firstly, I'm going to take you through our motivation. So what are we doing? We're examining backscatter systems in terms of localizing and communicating with microimplants in the human body, and we're doing that by examining previous papers in this area. We're going to analyze this and come to some conclusions in terms of the uses and advantages. So why is this important? Before I tell you that, I'm going to explain what backscatter communication is, just so you understand what we're talking about in our presentation. Backscatter systems are basically devices that make use of the many radio frequency signals that surround us. For example, the ones that come from mobile networks. And this means that these systems can exist without having to generate their own signals. So backscatter communication allows us to use existing wireless signals as both a source of power and a communication medium. Now, with the increase of IoT or Internet of Things devices, this technology is promising. This is because it allows devices to operate and communicate without the need for large batteries. The medical industry today is seeking new solutions for in-body and on-body devices that transfer data over wireless channels. We believe that this can have very promising healthcare applications. Next, I'm going to talk to you a bit about the theory behind backscatter systems. So how it works. Standard backscatter systems have three components: the backscatter transmitter, the receiver, and the carrier emitter. The backscatter transmitter reflects the signal from the emitter to the receiver. These devices can be passive or semi-passive. When they're passive, they rely solely on reflected energy. However, with the addition of a small internal power source, it makes them semi-passive. This addition is positive because it does make the device more reliable and eliminates access delays, but it does increase the overall size of the backscatter system, which can be vital in terms of the effectiveness of the system.
So next we're going to talk about applications. There are many prospective applications to in-body backscatter communication. However, the most predominant field in which this could be used would be the healthcare and medical industries. Applications could include more advanced pacemakers, which generate electric pulses for heartbeat regulations, microscale robots capable of operating in the bloodstream, or even smart pills capable of identifying abnormalities in the gastrointestinal tract. All these applications require implantable microtechnologies with low heat and radiation emissions, capable of communicating with each other and the outside world. Given that backscatter communication allows data exchange between miniature and low power budget devices, the implantation of these devices in either human flesh or clothing would be minimally invasive, which could greatly change the way doctors and patients see and experience health monitoring. Further applications in the healthcare system are visible on the slide, which include information registry, emergency evaluations, health monitoring, and lab analysis, which are all concepts that could be expedited with the use of in-body backscattering. Although healthcare is one of the spheres where this technology would have the greatest impact, the applications are not limited to this domain and could also be included in smartphones, smart homes, smart cities, as well as logistics and other healthcare applications. In-body emitters or sensors implanted in a large portion of the population could be used for data analysis and security concerns, and biomechanical applications, such as the Google contact lens, which is visible on the slide, are not necessarily related to healthcare, but still require miniature and low heat or radiation devices to become achievable goals and use in-body backscattering.
Now onto the challenges. One of the challenges faced by deep tissue backscatter devices is signal changes such as reflection, deflection, phase change, and attenuation. Here, the signal changes are caused by the fact that radio frequency signals travel 8 times slower in muscle than in air. A technique has been developed to address this issue, which is called remix, and Sammy is going to discuss it in more detail later. Another challenge faced by information transmission of in-body backscatter devices is the limitation of current data transmission technologies with the various applications of the devices. Different sources of radio frequency were explored to compare which source would fit best the uses of the devices. It was concluded that Wi-Fi and Bluetooth radios are better option for indoor use cases, whereas FM and TV towers are preferred for outdoor use cases. So this would require a single body to have various types of transmitters for devices to be constantly connected, which adds some interference and noises concerns. Another main challenge faced by the technology is the security of the devices. In order for in-body backscatter devices to be accepted, they would have to be fully secured and protected from any kind of mischievous attacks. This is necessary for the users to be protected from life-threatening scenarios, such as attackers taking control of pacemaker or installing malware that share a person's data and information. Some techniques have been developed to address this security concern. However, these approaches are currently limited to one-hop networks, which are networks where all devices can be reached directly from the aggregator. For this technology to be adopted, a algorithm would have to be devised to assure security for multi-hop networks.
So now we'll talk about the solutions. So we did research on new technologies that can be developed with backscattering communications. The approach we decided to explore was the remix technology. It is a new backscatter communication approach, which is ideal for deep tissue devices. It uses non-ideal circuit behavior to separate the backscatter reflection of the device from other reflections. Remix is made up of two main parts, a transceiver system and an in-body scatter module. The diagram on the right shows the device is set up in the body. The transceiver, highlighted by the blue triangle, is placed a few meters away from the patient, and the in-body modules are attached to the in-body device. We can also see the ambient source signal highlighted by the two pink triangles. The remix approach will solve some of the challenges Maxime had mentioned. The first challenge is that the reflections due to the surface interference overpower the signal from the backscatter device. The remix approach solves this problem as it separates the signals from the backscatter device. It does this by shifting the internal frequency. This allows signals to be identified and captured by the receiver without interference. The second challenge has to do with locating the device inside the body. This is a problem because signals don't move in a straight line, especially through muscles, as Maxime explained before. Thus, to predict the signal, the slight signal deviations caused by the muscle tissue, the remix approach uses a prediction algorithm. The algorithm first estimates the distance from the device as if the signal were to travel in air. Then the signal is modeled using piecewise linear segments based on different materials. Lastly, the algorithm optimizes the effective distance with linear segments to map the real signal parts. Just to conclude the presentation, backscattering communication devices offer promising solutions to power and offer communication between low-powered devices in many fields. One main challenge of this technology faces is when it is placed inside bodies, as this can cause signal deviations. The remix approach tries to solve this problem by using signal backscattering. However, this technology still faces many problems such as security and signal deflection. So these are the references we used for the presentation. Thank you.